Hello, welcome back to your Module 5. So we are now on your Unit 3, which is the application of influence lines, which we discussed in your Unit 1 and 2. Okay, so in this unit, these are your unit learning outcomes. So first is for us to determine the response due to a uniformly distributed load, and of course to determine the response due to a series of moving concentrated loads. Since if you will try to recall our discussion in Unit 1, we discussed only the actual response due to a concentrated load. Okay? Wherein, of course, if you will try to relate that one to the establishment or the drawing of your influence line, we will try to consider a unit load, okay, to make it general. And then once you have the actual load or actual value of a concentrated load, all you need to do is multiply the value of the load to the ordinate of your influence line, which is drawn from a unit load. However, what if that is now your load, your actual load is now not just a concentrated load, which is actually the actual cases, okay, actual cases when it comes to actual types of loading. Okay, so let's say you have a loading which is uniformly distributed load, then how are you going to use the influence line to calculate the actual response? And of course, when it comes to a multiple concentrated load, we call that one series of moving concentrated loads, since we are referring to moving loads, okay? Then how is that calculated also when it comes to that type of loading? So, let's start with the first type. When your loading is a uniformly distributed load, okay? So the response due to a UDL, okay, so that is a uniformly distributed load. The response due to a UDL is just the product of the load intensity W and the area of the influence line diagram under the load. So since we are referring here to a uniformly distributed load, we will have a uniform intensity of the loading all throughout, which is represented, let's say, as by the variable W. And then of course that W, all you need to do is multiply that one with the area, okay, under that UDL within your influence line. Okay, so that is how we will get the actual response of this uniformly distributed load. Just like your concentrated load, isn't it that all you need to do is multiply the intensity or the value of that concentrated load with the corresponding ordinate below that loading. In here, your loading now is a UDL, that is a distributed, so we will multiply that W, that is the intensity, okay, to the area under that loading. Okay, so let's say you have a multiple values. Okay, let's say that we have here a multiple values of W, variable values of W within the length. All you need to do is, of course, get the individual response due to the individual uniformly distributed load. Then all you need to do is submit. Okay, so again, the response is just the product of the intensity of the UDL with the area of your diagram under the load. So let's try to have an example for this. So the beam shown determine the maximum positive and negative moment at B due to a uniformly distributed live load of 2 kips per feet, and then a uniformly distributed dead load of 0.5 kip per feet. Okay, so if you will try to look at this beam, this is actually our example number 1 in your unit 1. So we will not be repeating, I will not repeat showing you the solution. So if you want to know, to recall or to check again the solution of establishing this influence line, all you need to do is proceed to your unit 1 example number 1. Okay, so we will now focus on how to make use of this this influence line to calculate the actual response if we have a loading of UDL. Okay, so the influence line for the internal moment at B will be used to determine the position of the variable load. Okay, if we say variable load, that is of course we are referring here to the live load, that will give the maximum position, maximum positive or negative response. Since of course if we say variable or live load, that live load is changing with respect to time. So unlike in dead load, that all you need to do is place that one on the position, and then all you need to do is you can actually use the equilibrium to calculate the response itself. However, since this is again a variable, it will change from time to time, then it means that that is a function of its position. So we can just put that as a function of x, since of course x is how we will determine or how we will describe the location or the position of the loading. Okay. So again, that is why we will be needing the influence line, since our loading, we have here the live load, which is a variable load. But at the same time, you should not forget about this, that we have a dead load. A dead load is of course not a moving load, it is a fixed load. Okay, so it is a combination of a fixed load and a moving load or a variable load. Okay, so the solution again of the influence line on how we establish this one is presented in your Unit 1 example number 1. Okay. So again, as you can see, it is shown here on the influence line that when the loading is within your A to C, then your moment, since we are referring here to the moment, okay, the internal moment at this point B here, which is at the midway of A to C, okay, will be positive when the loading is within AC, but then it will become negative when the loading will now be going to your segment C to E. Okay, this moment at B will now become negative when the loading is within this portion. So that is how we will figure out, okay, where we will place the live load for us to have the maximum positive or for us to get the maximum negative. Okay, so again, that is the use of your influence line. So let's try to calculate that one. So first, let's try to calculate the maximum positive. So it means maximum positive moment at B. Okay. So how are we going to orient the loading, or how are we going to position the loading? Is just, of course, let's try to understand that the dead load is a fixed load which is distributed all throughout the beam. Okay. It did not specify there that the dead load is just at a certain portion. Okay, so it is not just at a certain portion, so we will assume that that is within the entire length of the beam. And then of course, that is of course the 0.5 kip per feet. And then of course, we will try to position the live load, because again, as I've said, live load is a variable load, so it can be found at any position, okay, in different times. So however, since what we are after here is just the maximum positive, so we will try to locate where should be this live load situated for us to have the maximum possible moment at B. Since again, this is the outline of the response of the moment at B. Okay, so it says there that since we discussed a while ago that in a UDL, the response, the actual response, is the product of the intensity and the area. Therefore, we should locate, since we are after a maximum positive, we should locate our variable load to the position of the positive area. So let's try to lay a live load, which is 2 kip per feet, within that positive area of the influence line. That should be where the live load to be situated for us to have a positive, okay, for us to have the maximum possible positive moment at B. Since of course it's possible that you can project that 2 kip per feet all throughout the beam, but if we will do that, we will be having additional load within your negative portion. Therefore, if we will have that one, then there will be a decrease of the moment at B due to that negative response due to this negative area. So we will only try to locate our load within the positive, since again we are after a maximum positive. Okay, so if that's the case, then all we need to do is calculate the actual response, and again, since we are dealing with UDL, then all you need to do is multiply the intensity of the UDL with the area under that loading. So let's start with this portion A to C. So we have here two UDL, the UDL of the dead load and then the UDL of the live load. So of course, since of course they have the same coverage, we can add these two, 0.5 plus 2, okay, we can add that one, that will be a total of 2.5, that is the intensity, okay, total intensity of the UDL. Then multiply that one with the area of your diagram, which is below that loading, which is just a triangular shape, so we can actually get the area by 1/2 base times height. So the 1/2, and then the base there will be 20, okay, 10 feet will be 20, and then the height is 5, then that is for the portion of your A to C. However, we still have a loading that needs to be considered within the span CE. Okay, but we need also to take into consideration the sign of your area, okay, under that loading. So the area here is, of course, as you can see, the coordinate here is negative. So if we will try to get the area, that will be a negative, and then multiply that one with the intensity. So instead of carrying that negative within your 10, I'd rather put that one as the operation. Instead of plus, that will be minus. So minus the intensity, which is 0.5, and then the area. So still triangle, 1/2 base times height. Your base is 20, 20, a total of 40, and then your height is 10. So calculate this one, and put in your calculator. You will have a value which is 25 cubic feet. So that is what we calculated as the maximum possible positive, okay, maximum positive moment at B due to a dead load of 0.5 cubic feet and then a live load of 2 cubic per feet. Okay, so again, that is the possible scenario for us to have the maximum positive moment. So let's proceed with the next unknown or the next requirement, wherein we need also to calculate the maximum negative. So that will be our item number or letter B, maximum negative moment at B. So again, as you can see, we will be guided by this influence line. So for us to have the possible maximum, we will only load the variable load within the negative area of the influence line. Okay, so we will not be putting there on the positive because that will cancel out the negative, since what we're after is just the maximum negative. Okay, so but still, of course, we need to consider the dead load to be within the entire span, since that is, of course, stated on the problem as a dead load. Okay, so now the same thing. Let's start with A to C. A to C. So the only intensity that we can see here is the 0.5 due to the dead load. So 0.5 times the area of that is again 1/2 base times height, 20 times 5 times 1/2. And then of course that is positive, okay? That is positive since of course we have an area of positive. And then we have here the segments C to E, combination of the UDL, 0.5 and 2, that will be a total of 2.5. And it will be a negative since our area here projected below will be a negative. So negative 2.5 times the area, 1/2 base times height. So we will calculate that one as negative 475 cubic feet. So that is the possible maximum negative, okay, or maximum possible negative moment at B due to this loading. Okay, so that is the actual response due to a uniformly distributed load. Okay. How about if that is a series of moving concentrated loads? Okay, so again, in relation to what we discussed in your unit 1, that the actual response of a concentrated load, a single concentrated load, is the product of the load itself with the ordinate, okay, with the ordinate in your influence line. Then that relates with your series. If we say series, that is just combination of more than one concentrated load. So what happens on a single concentrated load happens on the other concentrated load. So, okay, the effect of each of the concentrated load will be just the product of the load itself with the corresponding ordinate within your influence line. However, since that is not just only one, so we need to consider the effect of all of the concentrated loads. Then all we need to do is summate that one, or get the total by summating. So that's it. So we will summate the product of the load with the ordinate of the influence line under that specific load itself. So in this case, so all we need to do is add the P1 times Y1, P2 times Y2, P3 times Y3. Okay, by the way, we will just discuss this one as a general, okay? Your response could be anything. That's why I put there R. That could be a reaction, that could be an internal shear, that could be an internal moment, or it could be in trusses, it could be an axial force, okay, or it could be a deflection. So again, any response, that is the same. So all we need to do is draw the influence line, of course, of the response that we are after, then of course apply this concept in your series of moving concentrated loads, or just like a while ago in your UDL, uniformly distributed load. Okay, so let's try to have an example for this. We call this one actually as field loads, okay. Most or one example of this series of concentrated loads or moving concentrated loads is what we call as the wheel loads. If you say wheel loads, that is a load due to a traffic or due to a truck, okay, imposed by its wheel, okay. Because of course, let's say for example this is the truck. The load of the truck will be transferred due to the contact of the wheels. So we sometimes call this one as a wheel load. Okay, this one important concept of wheel loads or series of moving loads is that the distances will be constant. Yes, it is known that this will be moving since that's a variable load, but the distances between them will be constant, since of course if that is representing a car, then the distance between the wheels will not change as it moves forward or as it moves across the structure. Okay, so that is what we should consider, that the distance between the concentrated loads will be fixed. Okay, so for example here, determine the maximum tensile stress formed at member CD when the truck passes through the bridge. The weight of the distribution, the weight distribution of the truck through its wheel is as shown. So this is of course the distribution of the total weight of the truck due to of course the loading, or I mean the orientation of the wheels. Okay, so as you can see, the total load will be the summation 16 plus 16, 32 plus 4 will be a total of 36. That is the total weight of the truck, but it will be distributed due to the 3 contact, which is the 3 contact of the wheels, and that is given as 60 kips, 16 kips, 16 kips, and 4 kips on the front wheel. So that is what we will be following, and that is given, okay, the dimension or the distances between these wheels is given to be 30 feet, the distance of the rear wheel with the intermediate, and then the intermediate to the front wheel will be a 14 feet. So we will assume that the car or the truck will be moving from point A to point G, or it will be passing going from left to right. Okay. So what we're after here is the response, or that is the member force of the member CD. So actually this example is also the example in your unit 2. Okay. So I will not be discussing again how we establish this influence line here. Rather, we will just be using this. Okay, but if you want to recall, or if you want again to check the solution on how we establish this influence line for your member CD, then all you need to do is proceed to your discussion of Unit 2. Okay, go to the example. So, since we are given here, we can actually now say that when the loading is within your joints A to E, your effect or the effect of that load to your CD will be positive. Since again, as I discussed on the trusses, that I will always assume, okay, my assumption for the sake of the discussion is always initially tension. Okay, so even if I will know that that will be a compression at that certain position of the member, then I will always assume that to be positive. Okay, so later on, the influence line diagram will dictate if that will become compression due to, of course, the location of your ordinate. If that is on the negative, then it means when the load is at that location, your member will be under compression. Okay, so again, positive, that will always be my assumption, positive will be the tension. Okay, so that's it. We have here your influence line. So again, when the load is within your joint A to E, your member CD will be under tension. But when that will be now within the joints E to J, to G, that will be now under compression. Okay. However, we are only after a maximum tensile. So we are going to investigate when that will be tension. Okay. So since this is a moving load, or this is a series of moving concentrated load, then at a certain time, the loading will be on within the maximum ordinate. Okay, so since we will assume that that is moving, we need to consider the possibility that the first load or all of the loads will be within this maximum ordinate. Since of course, we are going to figure out the maximum, the possible location of this loading that will give us the maximum tensile, since that is what is asked by the problem. So we are going to play around with the loading. Okay, let's try to move that one around in such a way that we will try to figure out where should be the position of that will be giving us the maximum tensile stress of your member CD. However, it is shown on a lot of examples, and of course calculation, if you will try to refer to references, that the maximum response will happen when we will try to locate, okay? When we will try to locate, when we will try to position the series of moving load in such a way that one of the concentrated load will be exactly on the location of the maximum ordinate, if we are after a maximum, of course. Okay, maximum response. If we are after a maximum positive, or that is in our case tensile, then we should locate these loadings on top of the maximum positive ordinate. However, if you are after a maximum compression, which is the negative, we will try to locate the loadings on top of the maximum negative. In this, in our case, that will be on joint G. Okay. However, we are on tensile, so we will try to locate that one. As you can see, the maximum ordinate is at joint C. So let's try to play around. What if your front wheel, okay, this is your front wheel. By the way, I did not draw the entire track so that it will not make our figure complicated, but we will still follow, okay, the orientation of the position of the loading, of course, since considering that is the track. So as you can see, 30 and 14 are the distances between these loadings. So if we will try to locate the front wheel, that is the forkip, exactly on top of C, for us to, of course, align that to the positive, maximum positive, then, of course, the location of the other wheels will follow, given that this is 30 between the intermediate and the rear, and 14 between the front and the intermediate. Okay, so that is how we will locate the rest. So if we will try to locate the front wheel exactly at C, it will end up that your rear wheel will not yet be within the range of the truss. So it means that we will not yet be considering the effect of the rear wheel, since still that is on the outside of the trusses, or the truss itself. Okay, so we will only consider the loads within the span itself. So now we have here the four kips within the maximum 0.75 ordinate. But since, as you can see, this is a 14 distance of the front with the intermediate, we cannot say that that is exactly at joint B. So we will not be using the value of the joint B, just like what we calculated previously on the example when we established this inference line. Rather, we will try to calculate the projection of that 14 feet, okay, which is, of course, by using ratio and proportion. Of course, that is now algebra, so it's up to you to check this one, okay. But if you will try to check that one, how we calculated, the ratio and proportion will happen within this right triangle here, okay. We know that that is the distance, isn't it? This is 6 at 15, so it means 15 each span. So 2 span is covering the A to C, so that is a total of 30 feet. And then we are after here at a distance 14 from this height, or that is at a distance 16 from the point. So by means of ratio and proportion, we can calculate that at a distance 14 feet from this point C, or at a distance 16 from this joint A, we can calculate that the corresponding ordinate will be 0.4. Okay, you can check that one. That is just ratio and proportion. Then that is what we will be multiplying with your 16. And then this 0.75 is what we will be multiplying with 4 kips. Again, if we will try to recall, the total response of a series of moving load will just be the summation, okay, of the product of each load with the corresponding ordinate. So that's it. That is what we will be following. Therefore, the actual response of CD will be the product of 4 times the ordinate, 0.75, and 16 plus times 0.4, the ordinate, okay, below that 16. Then that will be a total of 9.4 kips. Okay, so that will be our actual stress, or that is the tensile, since of course, as we can see, we ended up with positive. And that is what we expected, of course, since we will try to locate the load within the positive region. Okay, so that is for one of the possibilities. So let's call that one as the loading position 1. So what if now your 16, the intermediate wheel will now be the one on top of the maximum ordinate. Okay, so that will be our second possibility. Let's call that one as loading position 2. So still, the location of the 2 more wheels will follow, that your distances will be satisfied, 30 feet and 14 feet. So if your intermediate wheel will be within the joint C, your front wheel will be still 14 feet from C going forward, so that will not still be located exactly at joint D. Okay, so we need to project that one, and again by ratio and proportion, still this is 14 from the height, and then 16 from the 0 point. Then by ratio and proportion, that will be still 0.4. Okay. However, this time your 16 or your rear wheel is already within the coverage of the truss, or that is inside the truss. However, if you will try to project that one, the ordinate will still be 0. Why? Because still your rear wheel is resting directly on the support. So the support will carry directly that 16 kips. Okay? So again, that is what we tried to discuss on the concept of the inference line. Okay? When the load rests directly within the support will carry totally the loadings. Okay, that's why we will end up here with zero response. Okay, so now we have the corresponding ordinate of each of the loadings. Then all we need to do again is multiply and summate, and then that will be 44 times 0.4 positive, and of course 16 times 0.75, and then of course you do not need to show this, or if you want to show that, that will be 16 times 0. Since still it will not affect our value. So that will be a total of 13.6. Okay, so as you can see, in position 1, when the front wheel is exactly on top of the maximum, that will just be 9.4. But this time, if your intermediate wheel will be directly on top of the maximum, that will give us a little bit higher value, which is 13.6. And then we have still one more possibility, wherein your rear wheel will be the one to be on top of C. Okay, so that will be our third loading position, number 3. So again, it still follows, okay, the distance between the wheels will never change, because we will assume that that is still the truck moving. Okay, so if that is exactly at C, then your 16 is exactly at E, since the distance is 30. And if that is at E and at a distance 14, that is not again exactly at F. So again, we need to calculate by ratio and proportion. So as you can see, this is exactly at the maximum, and that is exactly at the support, so still 0. And then your front wheel will be, if you will try to project that one, at a distance 14 from this point. A while ago, the distance 14 is from the height of the triangle. This time, the distance 14 is from the vertex of the triangle. So that will be giving us a difference. But still, by ratio and proportion, we will end up here with negative 0.35, given that your total height here will be negative 0.75. Okay, so that's it. We need to do again is summate the product of the load with the ordinate. So let's start with 4. However, the ordinate here is within the negative. What does that mean? The effect of your front wheel is now compression to CD. Okay, so that is the meaning of that. Since again, your loading is within the region or within the location wherein the effect will be compression in your member CD. So actually that subtracts, okay, that subtracts within the total, since what we are after is the tensile. But still, let's try to calculate. So that 4, that front wheel is 4 multiplied to the ordinate 0.35 negative, so that will end up minus later on. And then 16, of course, that is within the support, so 0, and then the other 16 will be the maximum 0.75. So a total, okay, so as you can see, this will, a while ago, that added because it is a positive, but this time it will subtract, so it will become a little bit lesser. Therefore, we can conclude, okay, given the 3 values, 9.4, and then we have here 13.6, and then lastly 10.6. We can conclude that member CD will be of its maximum tensile stress when the intermediate wheel is at joint C. Okay, that is happening in this loading position 2. Okay, when your intermediate wheel is exactly at joint C, where the maximum ordinate happen, okay, then that will be giving us at the same time the value of the maximum tensile stress in your member CD to be 13.6 kips. Okay, so that is now the application of the influence line. Okay, that is how important your influence line is. Because if you do not want to use the influence line, then you need to, and you want to evaluate or you want to investigate the actual response or actual reactions and so on and so forth of a structure due to a variable load, then you really need to, what we call this one, do calculation in terms of equation, since of course it is moving. So again, that is how important your influence line is to actually outline, okay, for you to see where you should locate the loading for us to have the maximum negative or positive, if that is what we are after. It depends on, of course, what response we are after. Okay, so that is the application of the influence line. So thank you very much. If you have questions, you can ask that one below the video. You can comment that one, or of course you can ask that one on our next live meeting. So thank you very much for watching.